It's going to be very practical, hands-on. We'll spend some time with cloud, talking about the various resources that you have to use there for this kind of work. And then we'll drill down into Kafka streams and how they work, which we think is the most cutting edge and practical technology out there right now. So the lectures will be divided amongst the four of us. I'm Jeffrey Ricker, and we also will have lectures from Vladimir Kondratenko, who's the Chief Operating Officer of our company. And then Yuri will be giving most of the lectures focused on Scala, and Andre will be giving lectures regarding cloud. So these are the faces that you're going to be seeing over the semester. Any questions on the overall framework of the class? Is anybody in the wrong room? Maybe now's the time to leave. Let's joke. And I also want to say that we're very thrilled that so many of you chose this class as opposed to, I know you had choices and you picked this one, and we're very honored, and we're gonna do our best to make it worth your while. So with that, I'm gonna start on this lecture, which is a short history of big data and streaming programming technology. In other words, how did we get here? And I'll start, since we're talking about history, give a little history of myself, right? I graduated Tulane University in 1991 with a degree in robotics. They didn't actually have robotics back then, so it was a focus on robotics. It was mechanical engineering. Just focus on my experience in this realm. In 1996, I represented the United States Army in the High Performance Computing Modernization Program, which is a fancy word for supercomputers, back when supercomputers were a thing. In 1997, I worked on the Defense Advanced Research Project Agency, DARPA project called Shaolin, which was a system of systems. We would call that the Internet of Things today. And then in 1998, I founded my first startup called XML Solutions Corporation, where we were dealing with business to business, B2B e-commerce during the dot-com boom. Next startup was called Distributed Instruments. And there we were dealing with sensor data fusion. We were working with the United States Army, the United States Air Force, the National Geospatial Intelligence Agency, and other agencies on how do they take all the different sensor streams that they're dealing with and get one picture. How do we know that two sensors are looking at the same event? And oddly enough, a lot of the things we weren't able to do then because the cloud and big data did not exist yet. So we were hitting wall after wall trying to solve these things. But it seemed like we weren't the only ones. A lot of other companies were trying to solve these same problems that we were back in 2004, and we're going to talk about that. I didn't really dive deep into big data until 2013, where I was leading a big data team at Amazon that was generating all of their financial metrics. And by 2015, we founded this company. Vladimir is a co-founder, Paul Lyman is another co-founder, and we are focused on big data and the Internet of Things. So that gives you my background on, my experience, and maybe gives me some credibility in talking about the history of this technology with you. So our objective today is to provide a historical context of the technology evolution leading up to streaming big data. And it's my hope that by understanding how we got here, you can understand why these technologies are, what they're doing, and more importantly, where we're going. So hopefully by seeing how we got here, you'll be better equipped to see where we're going. And I think that is as much a valuable skill for a technologist as any. Not just knowing what you can do now, but what you're going to be able to do in the near future. So the agenda for this lecture today is really divided into 6 sections. We're going to talk about the history of high-performance computing, the history of open source software, the history of Hadoop and big data. Then we'll get into the history of functional programming and streaming programming. And then we'll wrap up with why was all this important and what does it get us? So, any questions on the agenda? And I don't have a camera on you guys, so if you're raising your hand, I can't see you.
Jeff, you have just enable on the screen list of attendees. You'll see it in the top right corner.
Say that again.
There is a list of attendees. They should show you the stream on your top left, top right corner.
Yeah, I see the attendees, but I don't see the stream. Oh, yeah, I see it now. Thank you. All righty. Okay, now I can see you guys. Thank you, Vladimir.
Anytime.
If you ever, wash out as a chief operating officer, you'll make a great AV technician. Just got that in your back pocket.
You can turn on your camera as well, so it gets more interactive.
Oops. All right.
It's the bottom.
Okay. Now do you see me?
Uh-huh.
All right. Cool. All right. So first off, history of high performance computing, and it starts with the ENIAC. I was going to have a quiz. Who knows the first computer? 1946, the ENIAC. Anybody know who built it? Anyone? Does the name von Neumann sound familiar? You guys didn't. I guess in a graduate school, you're not expecting this, Q&A thing. I'll try to keep it more graduate level. I apologize. So it starts in 1946, and you got to think, the first computer was the supercomputer. There was no differentiation. They were just awesome. The fact that they existed was awesome. But that quickly changed. By 1964, we have the first, what's considered the first supercomputer. It's the Control Data 6600. She's a lovely thing, isn't she? I mean, just screams cutting edge. I love the dials on the right side. But one of the key things here was why the 6600 was considered a supercomputer is because she's already starting to deal with parallel processing. That was the key. The idea that the only way that you scale is running in parallel. It's just a very fundamental, basic concept. And then Cray built his first supercomputer in 1976. This is a picture of the Cray 1. And we actually had one of these at one of the defense laboratories that I worked at. And they're really beautiful. They're cooled by liquid nitrogen. And the shape of the thing in a circle was purposeful because it was the shortest way to run the wires. So the Cray was looking for the shortest path of wires because that was going to impact his compute speed. And so he made it in this circular shape. And this thing is in modules. So it's like pieces of a pie stick together to make a supercomputer. And I guess this is another thing to point out that, computers, supercomputing, pushing the envelope has always been a high energy thing. This thing, the air conditioning unit to run the liquid nitrogen through this thing was as big as a semi truck. Very expensive. By 1991, when I started getting involved in this, we had evolved to thinking machines was starting to dominate. And a funny thing, just an anecdote here about this. Thinking machines was trying to break into the Department of Defense supercomputing. And really, back then, the US government was about the only entity in the world that could afford to buy one of these things. And Cray just owned the market. The thinking machines just could not get a contract. So they hired a retired general, 4-star general, to ask them why. And he comes in and he looks at it and he's like, you got no blinking lights. He's like, what? Like, have you never watched Star Trek? When you go on the bridge of Star Trek, there's blinking lights everywhere, right? Put some blinking lights on the front end of this thing. And the engineers are like, well, what the hell would that do? Like, trust me, just, and they go, well, what do they do? He goes, I don't care, just make them random. Just put blinking lights on the front of this thing. And honest to God, the next year they sold a bunch of them. The government came in and saw them and went, ooh, and bought millions of dollars worth of these things. So just keep that in mind. It's going to affect you. The customer doesn't understand when you're dealing with cutting edge technology like you guys will be when you leave here. The customer doesn't understand it, right? They're going to focus on what they understand. And sometimes you got to get them blinking lights to actually get them what they need. So about the same time in 1994, just as, these things are really coming into their own, something remarkable happened. And it's the Beowulf Cluster. And most people missed it. It wasn't until 5 or maybe 10 years later that the impact of what these guys did really sunk in to the industry. And what they did was they just took a bunch of off-the-shelf computers and networked them on a high-speed bus, what back then passed as a high-speed bus, and created a supercomputer. So instead of spending millions of dollars to create these custom computers, they just took off-the-shelf hardware. Now today, we take this kind of thing for granted, but somebody had to do it first, and these guys did. So supercomputers are still around. There is annually published a top 500 list. And for the past couple of years, this monster has been #1. This thing is called the Summit, and it sits in Oak Ridge National Laboratories in Tennessee for the Department of Energy. And it is a 4,356 nodes, each one with 22 core Power 9 and 6 NVIDIA Tesla V100 GPUs. So these things are monsters. And you're talking about, if you thought the Cray was hard to keep cool, there's a reason why this thing is sitting in Oak Ridge where there's really cheap electricity. This thing is a monster. But notice it's commercial hardware that they've used. So it's following, all the new supercomputers are following what was achieved with the Beowulf cluster. Thinking machines and Cray are out of business. So the history of supercomputing really is divided into 4 eras, to sum up. The first supercomputers were up until 1970, and then Cray, and really Cray came on the scene and dominated from 75 to 90. And then we got into the clustering era, and I didn't cover how Silicon Graphics and others started moving into that space, but they did. But then finally, we got into where we are now, still 18 years later, the GPU and hybrid era. Something big is coming soon. We've gone too long with the existing technology. And it may have already happened. What science fiction writer said that history is already, the future is already here, it's just not evenly distributed. So you've got to keep an eye on things like quantum computing. What's Lyman's favorite that he's always talking about? Neomorphic computing.
Yeah.
And so there are new chips. There's probably a half a dozen new chip technologies that are being experimented on. So since, I mean, real intense experimentation going on. And it'll be very interesting to see which one of those breaks through. The Beowulf incident may have already occurred, and the rest of us just haven't felt the impact of it yet. And why is this all happening? Well, you've all heard Moore's Law. I hope to God you didn't get to graduate level without hearing of Moore's Law. How there's an exponential growth in computing power. This is a log scale, right? So if this was done on a regular scale, it would look like a big hockey curve. And this thing has constantly been stepping forward, but we're starting to see it plateau on the CPU level. We're actually witnessing a slowdown in Moore's Law as far as CPU goes. But what's happened is it's shifted to GPU. This is a measure of what GPUs have been able to do in teraflops over the past few years. This is where the growth is in compute power. And this is where we're seeing all the machine learning frameworks, et cetera, move to. So TensorFlow doesn't work without GPUs. You can't get that level of machine learning without this kind of compute power. And it fits on your laptop. So that's the history of supercomputing. So I'm going to pause real quick to see if there are any questions on what we've covered there so far. All right. So next history that we're going to go through is open source software. And this is just as relevant as what's been going on with hardware. You just don't get to where we are today without this revolution that occurred. And it starts with this guy. Anybody know who this guy is? No? Thomas Jefferson. I hope you've heard of him. One of the founding fathers of the United States. And one of his very first jobs in the new government was to create the US Patent Office. And this is a picture of the very first patent, which is it's written by hand and signed by hand by George Washington and the Attorney General Randolph. It's pretty amazing how small the government was back then. And why am I mentioning this? Well, the way the US Patent Office exists is it's a quid pro quo, right? The US government, and it was revolutionary. What they set up was they said, you must divulge to us how your invention works. You must publish it to the world, show everybody how you built this thing. And in return, we will give you a protection, legal protection of that invention for 20 years. And the purpose where the founding fathers saw what was good for society was the idea was that you're going to go and show everybody else how you did it, and then somebody out there is going to be able to improve upon it. They're going to figure out a better way to do what you did. And then we'll give them a patent on that improvement, and then somebody else will improve yours, and somebody else will improve yours. So we encourage people to show us how they do it. So we're encouraging innovation, but we're rewarding, we've got to give them something for it, and that's patent protection. See how that works? And it's the key, it's absolutely key to technology innovation. None of the things that we're talking about would have happened without this kind of institution, encouraging it, facilitating it, protecting it. So we jump a couple of 100 years ahead of time to this guy. So 1984, and when I hear the year 1984, I think of the launch of the Mac. But even more important to what we're talking about was the launch of something called GNU by Richard Stallman of MIT. Now this guy, he couldn't be 180 degrees different from Thomas Jefferson. Stallman is a socialist, practically a communist. But he created this thing called GNU, which stands for GNU is not Unix. It's kind of a circular thing. But it was really the first open source software. And a couple of years later, he invented the licensing for this, which is the GPL, which became the first legal framework for dealing with open source software. A couple of years later, 1991, we have another guy. Does anybody know who this guy is? Does his face look familiar? Everyone's favorite Finn, Linus Torvald. And he invented Linux. So he created a Linux operating system that would run on the x86 chip. Then, a couple of years later, we have this guy. Anybody recognize him? Mark Anderson. And while working at the National Center for Supercomputing in the University of Illinois, he created and released open source a simple little program called the Mosaic browser, which was the single event that created the World Wide Web. Without a browser that you could download and use, there was no web. And it was, you can't overestimate the impact of what this guy did with that little program in 1993. By 1999, another key event occurred. There had been Apache had come out as the almost default web server, but the guys got together, and I don't expect anybody to know this guy. This is Roy Fielding. You may know his name. He's the guy that came up with REST. But he was one of the key founders of the Apache Foundation. But what they did was they created a legal institution with a framework that was governed by meritocracy that allowed these open source projects to have a home, to have a government, to have an infrastructure. And without that occurring, it's hard to see how we get projects like Hadoop to the level and stability and scope that they are today. So to sum up on this evolution, right? First, you have Richard Stallman. He starts the GNU project in 1984. By 1989, he's worked with lawyers and created the GPL. So now there are probably a dozen different open source licenses, but it was the first of its kind. Linus Torvald releases Linux in 91, Mosaic browser in 93. Netscape is released the next year. So is MySQL, the first open source SQL database. And 1996, Apache is launched. So by this time, you have the LAMP architecture, the open source architecture that's used to build most of the web. 1997, Eric Raymond publishes The Cathedral and the Bazaar. And what he did there was, and I highly recommend if you haven't read it to find it, you can download it for free. But The Cathedral of the Bazaar explains why open source works and how it will be an ongoing dominant factor in software development, which nobody was really convinced. They were still, you know, we're at the beginning of the dot-com boom. Nobody knows where this is going, how it's working. Open source is still very brand new, and most corporations are shunning it, or they're bringing it in and treating it like it's atomic waste. Okay, you can bring that thing in here, but just keep it away from all our other production systems, right? But after 97, after Eric's paper starts to get read by CEOs and CIOs, people start to understand that this isn't a fluke. And by 1999, and this is a serious watershed event, not only does Apache Foundation create it, but IBM announces that they're going to invest $1 billion in Linux. And that's when the whole industry sat up and said, okay, this is real. And all that has to happen before we get to 2006, when Hadoop Incubator project is launched. So any questions on the history of how we got to open source? All right. And any observations, anything people want to share, like, well, how important was this or what? I mean, feel free. All right. All right, so now we'll get into Hadoop, how we actually got to the technology that we're going to be dealing with. And in 1997, a guy named Doug Cutting started a project called Lucene. Now, this is before the Apache Foundation exists. He's just, you didn't even have infrastructure really. About all you had was SourceForge on the internet to work on something like this. But he creates something called a full text search library. Now, what is that? Well, it's something that analyzes ordinary text for the purpose of building an index. And why would he want to do that? Well, because the World Wide Web is growing and people are finding a hard time finding stuff. So Yahoo was the first real search engine. And it wasn't really a search engine, it was an indexing engine. They were still thinking in terms of how a card catalog used to work in a library. So in the United States, we have the Dewey Decimal System, or the Library of Congress system of indexing books. And you just kind of create this taxonomy of subjects, and then you kind of put the books in that. So, you know, you have like natural history and political history, and under political history, or just even history, you would have, you know, Eastern history and Western history, and then within Western history, you would have medieval and ancient and modern, right? And so they just keep dividing it further and further, and then finally you get down to, you know, modern German history, and you can find something on you know, Lindenberg is how you would find that. Well, Yahoo built their website like that, and they were acting as librarians. They were finding new websites and sticking them into these subjects, and people were like, oh wow, I can actually find these things. But it just kept growing and growing and growing. So Doug Cutting was figuring out that, you know, we're going to have to figure out some way to do this automatically, right? And so he was working on a project to do this full text search. And then it got added to another project that called Nutch, where it was doing web crawling, what we now call web crawling. So instead of you manually pointing the application at a website, it was crawling through, finding the links to other websites, and then going to those other pages and indexing them. And then within indexing it, it would find new links to other pages and go to them. So like a spider crawling across a web, the Nutch was a web crawler that was supposed to automatically start indexing the World Wide Web. Pretty revolutionary concept. Luckily for him, he's just some guy working in a university on this part-time. There's another guy working on it at Google. But let me explain to you what these guys are facing at this time, and we face it still today. Are you guys familiar with the legend of Paul Pesum? All right, so the it's an Indian legend where they're playing chess for stakes, and the one guy says, "Look, all you have to do if I win, you just have to pay me grains of rice, so that on a chessboard. But what I want you to do is, on the first chessboard slot, put 1 grain, and then double it for each new chessboard piece." And the king goes, "Oh, well, yeah, I can do that. I mean, that's nothing." But he didn't understand exponential growth, right? So I don't know if you can see this on the screen, but yeah, you start with 1 grain of rice. In the second square, you got 2 grains of rice, and then 4, and then 8. And then by the time you get to the third row, you've got 8 million, right? By the time you get to by halfway across the board, you're at 2 gig. Turns out by the time you get to the last square of it, it's enough rice to cover all of India about 5 feet deep, right? It's a lot of rice. And so this is the concept of exponential growth. Another example that we can use is if you had pennies or coins, and you had 1 coin, and then you doubled the stack, and then you doubled the stack, and then doubled the stack. In less than a month, the stack would reach the moon. Right? Exponential growth is hard for humans to get their heads around because it starts off so slow and it just gets so big. Well, that's what the internet was doing. That's what the World Wide Web was doing and is still doing today. So Lucene and Nutch project were facing a daunting problem that Yahoo just really wasn't intellectually engaged in. They couldn't see it until it was too late. But another group of guys did see it, and they were the founders of Google, and now they're billionaires. And for some reason, they started publishing some of their key technologies. I don't know why, but they did, and God bless them for it. One of the first papers that they published, and you can find these online still today and go read them, and they're written just like any other scientific paper. The first one is the Google file system. So the guys that are working on Lucene are starting to face a challenge of where do we put all this data, right? By the way, how long does this class go to?
Till 9.
Till 9? All right. 9:30 or 9?
9.
9. Okay, so I got to pick it up. They were starting to fill up the computer. They couldn't add enough disk drives into the computer that they were using to serve their Lucene Nutch software. Well, Google had faced the problem the same way. So they had created a way to make the disk drives of several computers look like one big disk drive, and they called it the Google file system. But it was more important than that, because one of the key things they took in place is Google was trying to buy more and more expensive hard drives because failure was an issue. And they finally just flipped it on its head. They said, hard drives, no matter how expensive, are going to fail. So don't fight it, embrace it. Just build a system that assumes that hard drives will fail. And that's what the Google file system did. So it created a schemaless, durable, component failure, and automatic rebalancing. And what it looks like is this, right? So they have this master server, which has shadow masters for high availability. And then it has these chunk servers. And then it takes a file, and these are very big files, and it divides them into standard sizes called chunks. And then it distributes the chunks across the chunk servers. But not only that, it makes a duplicate copy or a redundant copy of each chunk and puts it on a different drive, right? So that if any one drive is lost, you know you have another copy on another drive of everything that was on that. Now, this is kind of the way, it wasn't anything spectacular in the thinking because this is the way RAID works. But this is like RAID across multiple machines. And instead of a standard chunk on a disk drive being, I don't know what it is these days, you know, a couple of K, these chunks are, 60 megabytes, right? But so the guys see this at Lucene and they're like, damn straight, let's do that. And they implement it. And then while they're implementing that, they realize that they can't do all the processing. They got to parallel the processing of their crawling. And they're struggling with how to solve that. Well, lo and behold, Google publishes another paper called Google MapReduce. And Google MapReduce does three amazing things. First off, it shows you how to very simply parallelize the computation. And we're going to go much deeper into these concepts at a future lecture. So I'm just going to go over it pretty quick here. It distributes and it is fault tolerant. So it brings fault tolerance to the compute level like they did for the storage level. And here's a big thing. They don't move the data to the compute. They move the compute to the data. And that was really the big breakthrough. So these guys at Lucene and Notch, and by the way, here's a drawing of MapReduce. And like I said, we're going to go into it in much more detail. First off, how many people have actually done MapReduce already in the class? Maybe a third of you? Okay. So real quick, how MapReduce works, and again, we'll dive into this in the future. You have an input, and you split the input, and then you run processing on each split of the input. And what it does, the first step is map it. So this is a simple word count. So it says, okay, on the first file, there's one instance of deer, one instance of bear, one instance of river, et cetera, et cetera, et cetera. Then it shuffles, and it says, okay, send all the bear instances from every mapping to one, all the car instances from every mapping to another, et cetera. And then you reduce it. And so you have a reducer that gets all the bear, a reducer that gets all the car, a reducer gets all the deer. And now you can merge those final results, right? Very simple pattern, but my God, it can be applied over and over and over again. So these guys did that. So 1997, they start Lucene. 2001, it becomes an Apache project, and it expands to Notch. Then in 2003, Google publishes file system. So the next year, they have the Notch file system. And by the way, same year, Scala is released. And then later that year, they publish MapReduce. And by the middle of the next year, they've integrated MapReduce into Notch. And so that's when they decided, hey, this is much more generic than just web crawling. This needs to be a separate program. So they, here we go. Yes, here we go. So the next year, they release Hadoop as its own project, as an incubator project. That year, in 2006, Google still keeps publishing these papers. They're so far ahead of the rest of the industry that the rest of them are doing catch up. In 2007, in 2006, Yahoo realizes this is the technology they need to stay alive, and they start adopting Hadoop. And then these other technologies start coming out. HBase, which is a NoSQL database, which is based on Bigtable, is released in 2008. Zookeeper is released. Zookeeper is, and this is, again, they keep finding things that are common and generic and spinning them out so they can be reused. Zookeeper, we'll get into what Zookeeper does in another lecture. 2008, Pig and Hive are released. These are scripting languages that go on top of MapReduce. So instead of having to write MapReduce code, you can write these scripts that create your MapReduce code. And then by 2012, you know, Hadoop is a real thing. It's running in real production. Yahoo announces a 42,000 node cluster. And then Yarn becomes a separate project. So as much as MapReduce was interesting, the real technologies that come out of this are Yarn and HDFS. What they realized is what we're doing with MapReduce is we're sharing resources. We're doing cluster resource management. So just as they abstracted MapReduce out of Lucene and Nutch, they eventually figured out and they abstracted resource management out of MapReduce. And so this step that occurred in 2012 was just as big as the initial step, because Yarn enabled so many other frameworks to explode onto the scene. Yarn, by the way, stands for yet another resource manager. People can't spell. But. And HDFS, that's the Hadoop distributed file system. So that's what enables you to treat a whole bunch of computers, all the disk drives, as one big disk drive. And Yarn allows you to treat all the CPUs and memory as one big computer. And that's how you have these distributed frameworks. So any questions on the evolution of Hadoop and how we got there and why we got there? I mean, really, this technology, where did big data come from? It came from the World Wide Web. There was no big data before that. It just didn't exist. The problem didn't have to be solved before. And that's why people have been dealing with parallel processing and streaming processing at universities and defense labs for a long, long time. But it never went mainstream. It wasn't until corporations were dealing with this, and they were dealing with it because of the internet, that all this stuff left the universities, left the laboratories, and went mainstream. So the next history that we're going to cover is functional programming. And it starts with this guy, Gottfried von Leibniz. Do I hear a boo? No, you guys aren't. You guys like Leibniz? You're not Newton fans? I'm a Newton guy. I root for Newton as opposed to Leibniz. But the monad stuff I just never got. But he did get us thinking about this. And he had this idea called create a universal language in which all possible problems can be stated and find decision method to solve all those problems stated in a universal language. Now, it's called the Entscheidungsproblem. Now, he was absolutely wrong. No such thing exists. But by challenging us to say, you know, does it exist? He caused us to move much further. And it's amazing how these things all happen to occur at once, because in the exact same year, two different guys came up with two different solutions to the Entscheidungsproblem. Both of them proving that it can't be done, but at the same time, showing what could be done. And the one guy is Alonzo Church. He's the guy on the left. And the other guy is Alan Turing, the guy on the right. Now, Turing and Church went at it in completely different ways. And we still see this two-way thinking today. It's almost like the duality of you can treat it as a particle or a wave. You guys familiar with that in physics, right? We model it as a wave or we model it as a particle. They're both correct. It's just whichever model is more effective in whatever problem you're trying to solve, right? Because it is a lot like a wave and it is a lot like a particle. So the Turing machine and Lambda Calculus do the exact same thing, solve the exact same problem in just a completely different way. But they're interchangeable. Now, you guys are familiar with Turing machines. You're sitting in front of one, right? Your laptop. It's the foundation of digital computers. It's what von Neumann used to build that ENIAC in 1946, was Turing's paper on the Turing machine. But Church's Lambda Calculus is, if Turing was the father of the hardware, Church was the father of the software. So Lambda Calculus is a formal system of mathematical logic for expressing computation based on functional abstraction and application, blah, blah, blah. You guys can read this, right? I like the other definition better. It's the smallest universal programming language in the world. The Lambda Calculus consists of a single transformation rule, which is variable substitution, and a single function definition scheme, right? Anybody used Lambda Calculus in your classes? Anybody had a class on Lambda Calculus? All right. So it's been a long, long time since I took mathematical logic. So forgive me if I get some of this stuff wrong. But for those of you that haven't had it, here's two simple examples, right? You have this first line, which is, it looks like Lambda Calculus. It also looks like a programming language, right? And you say, first of, sort, append, dog, rabbit, sort, mouse, cat. And the parentheses show you the scope of your efforts. So the first thing we do is we reduce the sort, mouse, and cat. So now it says, okay, now it's cat and mouse. And then the next thing we do is we reduce the append statement. So dog, rabbit, cat, and mouse become one list. And then we reduce the sort command. So now the appended list is sorted. So we have cat, dog, mouse, and rabbit. And then finally, we take the first of that list, which is cat. See how that works? That's a very simple example of Lambda Calculus. And it should look very similar to the programming that you've done. Another one is mathematics. You've done this all your life, you know, that you have an order of functions that you have to reduce to get to the answer. If you didn't follow them in the right order, you'd come up with a different answer, right? If you added 8 plus 5 before you multiplied by 3, the answer becomes very different, right? So Lisp was the first programming language based on Lambda Calculus. And this is an example of how you do factorial in Lisp. Can you guys see that? I hope the text is big enough.
Yep.
Right? It looks exactly like Lambda Calculus because it is Lambda Calculus. Now, oddly enough, Lisp was the second programming language available for computers. And remember, first with the ENIAC, there wasn't any programming. They were actually changing the wiring, the physical wiring of the computer. That's why we call them bugs, because when the program wouldn't work, they would go inside the machine and find that some cockroach had shorted some circuit. And they had to remove the bugs from the programming to get it to work. By the time, then we have to deal with assembly language. And by the time we get to the 60s, computers are complex enough where they can actually write programming languages. Lisp was the second programming language. Anybody know what the first programming language was? You know what, Vladimir, we're going to have to bring stickers or something to reward participation. Nobody? Fortran, all right? And we'll get into the differences between those, but I think it's very interesting that procedural and functional procedural programming only preceded functional programming by a year. It's been around for a while. Now, so here's a history of the functional programming languages, an overview. So in 1932, Church introduces Lambda Calculus. 1958, McCarthy publishes Lisp. In 1970, a commercial version of Lisp is released called Scheme, which is with us today. Erlang came out in 86, Haskell in 90, JavaScript in 1995. JavaScript is a functional programming language. It's the most universal. Although most of the people that use it are hackers, not engineers, and they don't use it as a functional programming language. But it is possible. Scala, which you're going to be learning in this class, was introduced in 2004. F#, which is the Microsoft program. Scala runs on the JVM, which you're going to learn about, and F# runs on the Microsoft platform. So it compiles down the same way as C# and Visual Basic. And then Clojure is probably the latest functional programming language. And all, not to dumb it down, but Clojure is simply Lisp running on a JVM. All right. Now, maybe I should have started this section with this slide, which is, what do we mean by functional programming? Well, there are different programming paradigms. There are different ways to program, to think about how a program should work and how it should be put together. The first ones were imperative programming, which was literally changing the state emphatically. The moving the wires around inside of an ENIAC was imperative programming. Machine language coding, where you're doing shifts and pops and pushes, that's imperative programming. That evolved to structured programming, where you actually start getting things like Fortran. And then you get to procedural programming, where instead of having just this big, long program, step by step, you start breaking the programming into sections called procedures. And procedures just call other procedures. It's way for a human to break up a scroll. Think of structured programming to procedural programming is like going from a scroll to pages in a book, right? Before we had these big long scroll manuscripts in the Middle Ages, and it just continued on and on and on. And then we found out, it's much easier to deal with a book. And so COBOL was probably the most known procedural program. Then you have object-oriented programming, which is the dominant programming language paradigm used today. And I believe the reason why it dominates is because of that event that occurred in 1984, which was the Mac, right? The Mac introduced graphical user interfaces to the public. The mouse and the menu and the clicking and the scrolling, right? So before that, screens had been pretty text-based and pretty straightforward, menu-driven. Well, the complexity of creating those GUIs in a procedural format will kill you. I mean, and people struggled to do it back at that time. So object-oriented programming was the only way to get your head around and manage graphical user interface development. And we just took that paradigm and we started applying it everywhere, which may or may not have been a good thing. Some other paradigms that are out there: event-driven, declarative, reactive, and functional. And we're going to be focused on functional for most of this semester, but we'll be touching on event-driven as well. They kind of dovetail, as you'll see. Now, this is just a high-level programming paradigms. If you go to, I don't know, Wikipedia and look it up, you'll find that there are many, many more types of paradigms. And then these paradigms get divided into further sub-paradigms, et cetera. So this is an oversimplification, but it gives you an idea. So any question on the evolution of functional programming, the history of it, and how we got here? I think the take,
You can hear me?
Yes.
Because I'm not sure about, okay. Do you think object-oriented paradigm now is so popular? My reason is that it's used in math. Maybe it's, maybe my reason is that people think in this manner. It's easy to work with this paradigm, with this hierarchy. Usually, when we, for example, when somebody wants to describe idea about object-oriented paradigms, usually use example of cars, and it's like oral nature to think in this manner. I mean, in functional programming, it's not very common way to think, but object-oriented even in our life, and maybe it's main reason why it dominates at the moment.
That's a very good question, a very good point. Is it nature or nurture? So I'll rephrase your question. You know, if I heard you correctly, you said maybe object-oriented programming is dominating because this is the way we think. Well, that may be true. It may be by nature, or it may be by nurture, meaning this is how you're taught programming, this is how you're introduced to programming, and everybody talks about it this way. And so you mentally start to think this way. You start to apply these patterns. And really, these are about patterns, you know. In engineering, your mental patterns are your toolbox, right? You immediately, when you look at a problem, you immediately start applying, you pull out the, okay, what are my objects? So that's your hammer. And then, you know, what is my relational data structure? How do I normalize my relational data structure? You know, because I'm thinking in SQL databases. But these are mental patterns. And when you force yourself to start thinking of the problem in different ways, it's hard, right? You start thinking about, okay, how would I do this in a NoSQL database? You start designing things completely different than you would in a relational database. And you struggle with it, but then suddenly certain problems become very easy. So much easier than they were before. Not all problems, but some of them. You know, I'm old enough to have gone through the transition of procedural to object-oriented. When you first learned programming language back in the 80s, you were taught BASIC or Fortran, and it was procedural based. And then introducing objects was very hard, and some people never got it. They would just create one big object with one big method, and it was the procedure, right? And they were out constantly asking, how do I put a go-to statement in here? You don't, right? So, it required you to change the way you think about the problem and start thinking in objects. And then you saw, oh, well, this pattern is very useful. I can apply it again and again and again in all these different places. But sometimes you start getting into it and you're like, oh, this is really hard. Trying to get these objects to solve this problem is not working. And that's where functional programming, streaming programming, event-based programming, reactive programming, actor-based programming, you start to see that you can solve, they don't obsolete each other. and we'll talk about that in a minute, but it's not that one of these is the way to go, right? That's my key. They each have their purposes. So don't treat these as religion. Treat them as tools in a toolbox. All right. But
Yeah,
very good point.
Can I have an argument?
Well, we got one more section to go in 20 minutes. So
I believe in you. So to this topic, to this question, like about nurturing or nature, what we noticed in our experience dealing with functional programming, engineers that were never taught object-oriented programming, adopting functional way easier. That's like, it creates a stereotype for you. Object-oriented, it's not, it doesn't mean it's a natural way you always think of it. You'll think of it in some cases, but not always. That's why sometimes it's even make it worse if you study object-oriented.
yeah, the only way I was able to adopt it faster is because I learned Lisp back in college. And I immediately saw, oh, this is Lisp processing, I get it. Whereas if you'd been dealing with object-oriented, it's a learning curve. You got to change the way you think about the problem. All right, stream programming, last section. So, arose by any other name. Anybody think? No, would smell just as sweet. Shakespeare. They don't teach you Shakespeare, do they? We have to take a whole class on it. So there's many different names for this: stream programming, stream processing, real-time analytics, streaming analytics, complex event processing, event processing. Some people argue that there are differences in this. Yeah, when you start getting into the minutia, but they're all pretty much solving the same problem. So we call it stream processing now, but complex event processing's been around for a while. In fact, people started looking at this problem right after the dot-com boom. The first project that I'm aware of was out of Carnegie Mellon called Aurora, which evolved into Borealis. That was very clever of them. And then the first mainstream one that I've seen was Apama, and then Esper. Esper was an open source complex event processing engine. They followed they have a commercial version, an open source version. And this is where I saw companies start to use this technology. And 2011, Apache released S4, which is kind of, it reaches the height of its capability at the same moment it's obsolete, oddly enough. So, because 2011 is about the same time Storm and Spark are released. Now, a complex event processing is it's a very simple concept to explain, but it's a hell of a problem to try to program. So let's say we're writing a program that's listening for a bell ring. That's pretty, or a button push, right? That's falling off a log, right? But then let's instead say we're listening for a button pushed 3 times within 10 seconds. That's a little bit different, right? Because you have this stream of events, and then you have this 10-second window that's moving along that stream of events. So if you have a button pushed at time 1, and then you have another button pushed at time 8, and then you have another button pushed at time 11, you haven't had 3 button pushes in 10 seconds, right? But now you have a button pushed at time 12, you have, right? So that's the most simple complex event processing example I can think of. which is you're looking for 3 distinct events to fall within a certain time frame. But these things become more and more complicated. And where they show up is in business workflows or in machine processing, right? So you say, you're managing the production of steel, right? And steel, you have to raise the temperature up to a certain state and it has to maintain that state and then it goes down to a certain state. Or let's say you're observing wine shipment or some other product that is temperature sensitive. And it says it cannot go above the temperature of 40 degrees Celsius for more than 15 minutes. Otherwise, you have to throw it away, right? So you got to monitor this thing over time for an event that would occur for a period of time. So that's CEP. And it's all stream-based programming. So the concepts that we're applying started to be evolved in these other frameworks. And about the same time, MapReduce. So you can think of MapReduce as kind of a stream, right? But it's taking things and it's flowing them, you know, shipping them here, there, and everywhere, splitting and then mapping and then shuffling and then reducing. There's a hell of a lot of communication that's going on in MapReduce, but it's really batch, right? It has a beginning and an end. You have a finite set of input, you run it through this process, and it has a finite output. So yeah, even though there's a lot of communication going on, it's not stream programming. So where the change in stream programming occurred, however, that you're dealing with today is caused by MapReduce. So yeah, you have this MapReduce project and you're like, oh, I'm done. But that's not how things started to work. I'm not gonna deal with that slide. What happened was, when you actually started using MapReduce in the corporation, is that you would have this MapReduce job, and then you have to run this other MapReduce job on the output of the previous MapReduce job. And then you have another MapReduce job run on the previous output of that one. In the meantime, you're running another MapReduce job on another input. And then when you get to the step 4, you need to combine those 2 inputs for another MapReduce job, right? So you start getting these trees. And this diagram here of a Luigi task status is pretty typical of the way these production systems started to look for MapReduce, where each one of those circles is a different MapReduce job or a different data source, a different data result, and the lines are the MapReduce jobs between them, all right? And so the industry, the open source community started creating all these different workflows for handling this. Uzi was probably the most common, but Luigi, Azkaban, Airflow, Pinball, Cascade, TaskFlow, these are all different projects that were created by different corporations and then released into open source to solve this same problem. How do you chain a whole bunch of MapReduce jobs together and manage them? And people are starting to pull their hair out. And then in 2011, guy invents Storm. And he's like, why are we dealing with a stream as a whole bunch of sequence of batch? It doesn't make any sense to me. Why do we have to finish this job completely before we start the next job and then we do the next job? Why don't we just flow this like water? And he created this Apache Storm, which was the first modern streaming programming framework. And it's still around today, and it's still doing some amazing stuff. But that unleashed a whole other people to start thinking, right? So 2014, Apache Spark came along. And Spark says, you know, the biggest slowdown to MapReduce is the fact that you're writing to disk at all these steps, right? You read from the disk, and then you shuffle and you write to disk, and then you read from the shuffle from the disk, and then you write to the reduce to the disk. And then you start a whole nother thing again from reading from disk to writing to disk as you chain these things along. How about instead of writing to disk, we spill to disk and we just keep it in memory? And lo and behold, Spark was able to get 10 times performance improvement on these processes. And when you're spending, when these jobs start getting bigger and bigger and bigger, and you're wondering how the hell am I going to get this done in an 8-hour period, because the business needs the numbers, and they're already spending millions of dollars on hardware. 10 times improvement was a godsend, right? So companies really jumped at Spark. But there were so many more that came out. Samza, Flink, NiFi, Gearpump, Apex, Kafka Streams, and Akka Streams all came out about the same time, because everybody was looking at the same problem. NiFi is one of the more interesting ones. It solves the problem a little different, and I don't think we'll be covering NiFi in detail in this course. I think Vladimir will cover it when he talks about the landscape of technologies. But NiFi came out of the National Security Agency of the United States, NSA, which is they're the ones that monitor all the communications all over the globe. So these guys are collecting telephone calls and radio broadcasts and all that stuff from all over the world, and then sending it to a big data center in a secret undisclosed location. And how do they handle all that reliably and at scale? Well, they called it Niagara Files, and they shortened it to NiFi, and they released it open source. So that's where that thing came from. You're looking for something that's bulletproof and scalable, then the US National Security Agency is a good source. All right, so, and we got 10 more minutes. I've got to cover a couple of key things. I talk about how fast this stuff is moving. 2013, Lambda architecture is introduced. And so, as I said, Hadoop is a batch process. It has a beginning and an end. And usually people would start it and they would run it for 8 hours, right? And they keep running it over and over again, recalculate everything over and over again. But some people started saying, I can't wait 8 hours. I need to see the deltas during the day. So they added a streaming layer to it. They would append Spark or Storm or Flink or something to it so that they would have the batched and then the deltas in the streaming. They called it Lambda architecture. And this was pretty exciting. And companies started spending a lot of money on this. But 2015, it's already obsolete because the guys at Confluent have introduced Kappa architecture. And that's just how fast this industry is moving. You know, you have this huge breakthrough called Lambda architecture, which has nothing to do with Lambda Calculus, by the way. And these corporations start spending millions implementing it. And by the time they get it deployed, or maybe they're even halfway through, and some of them just heard about it, it's obsoleted by another technology and implementing Kappa architecture, where they say, you don't need the batch process at all. Let me show you how you can do it just through streaming. And that's what we're going to spend our class learning about this. So this is kind of a teaser of where we're going with in the lecture. So 5 minutes I got left to tell you about why is all this stuff important and what does it mean? And it's the fact that the only constant is change. That's what I want to convey to you. We're going to show you in this semester a snapshot of where we are. It's moving so fast. You've got to be able to see where we've been, and so you can know where we're going and keep up with it. So a few metaphors to deal with. First off is the pie metaphor. Why are there so many technologies out there? And why do they keep coming up? Why can't we just pick some technologies and deal with it? Well, think of each of these different technologies as a slice of a pie. And the pie is the problems that we're solving. And where two pie slices meet, neither one of the technologies really solves that problem very well. But you have to make do, right? So you shove a square peg into a round hole. Well, this pie is constantly expanding. It's expanding at an exponential rate. And those boundaries between two pie slices become gaps. And a new technology arises to fill that gap. You understand? Does that metaphor make sense? And this just keeps happening over and over and over again, right? So I call it the pie metaphor. And you got to watch for it. You got to watch for when something becomes a gap and anticipate that something's going to fill that gap, or be the guy or gal that fills it for the rest of the world, and make your own open source project in your own name in the industry. The other one is a tree metaphor. And whereas there's really only one core, and that is the Turing machine or the Lambda Calculus, right? They're the same thing. That's everything that you deal with is instances of either Lambda Calculus or Turing machine. But from there, you start getting, these programming paradigms. And from there, you get these nuances of the paradigms. And that trunk becomes branches, which become leaves. And sometimes it's it's not sometimes. It's very easy to get distracted by all the leaves. So as engineers, as scientists, you need to focus, you need to be able to identify the trunks and the branches of these technologies and focus on how things are common instead of how they're different. Another metaphor that we see is the pendulum swing. The market oscillates back and forth. It goes from centralized to decentralized, from structured to unstructured, from consolidated to fractured, and back again. So I give you an example. When first job out of the government, working at this laboratory, and they were going through this huge effort. Says, we're going to split out the research arm from the logistics arm. This is a big deal. So the laboratories will report through a separate reporting structure from the logistics of the Army. Wow, let's get this done. This makes a lot of sense. Let's do this. Big effort. The general that I was working for drops a folder on my desk. He's like, read that tonight, because I was really gung-ho about this. This was a fundamental change that was going to make a difference. And what he showed me was 10 years earlier was the plan to take research and put it under the logistics arm because it wasn't working. And then 10 years before that was a plan to remove research from logistics because it wasn't working. And 10 years before that was a plan to put research under logistics because it wasn't working. You see what I'm saying? They were just going through these 10-year cycles of merging and splitting and merging and splitting. And every time somebody got there, most of the people thought it was a brand new idea that had never been tried before, right? We're seeing that with the market. It used to be that all the computing was centralized in mainframes, and you had to do time sharing on it. And then it got pushed out to the desktop. And the time sharing and mainframe was a bad idea. We have distributed. And then you come to the cloud computing and big data. And guess what? These clusters are big mainframes that people have to time share their big data jobs on. It's exactly like mainframes. And now the pendulum swinging back again, the fog. That's where we're seeing, as our company is seeing the most traction, is getting away from the cloud and back to the edge. See what I mean? It's going to constantly swing back and forth. Just know it. And the hype cycle. Have you guys seen this? Gartner's hype cycle. Every new technology they figured goes through this thing. First, you have this triggered innovation event, and it quickly goes to this peak of inflated expectations. Blockchain is going to change the world. Big data is going to change the world. The Internet of Things is going to change the world. Buzzword here is going to change the world. And then people realize this shit doesn't work. I can't get this to work. This isn't doing anything. This is just a big pain in the ass. I can't. Now, what am I spending all this money on? You guys haven't showed me anything. But some people push through. And it didn't change the world, but it did that one thing that it's really good at. It made a lot better. And it made some people lives much easier, and it made some people much richer in the process. And that's where you get to the plateau of productivity. And every year they publish this thing, right? And the things move along the hype cycle at different rates of speed, right? So check this out once a year, the Gartner hype cycle, and see where the technology your customer is on it. It'll give you some perspective. And then finally, I could sum it up this way. Build wagons, not houses, right? Don't think that you've reached the promised land, that this technology that you're dealing with right now is where you're going to spend the rest of your life. You're going to have to keep moving. The frontier is constantly moving. So keep in the wagon, keep moving west, stay abreast of it. All right, well, that's it. And I ended a little bit late. Any questions?
Also, questions can be placed in Slack channel as well.
Yes. So this is the theoretical part of the lecture. I'll be giving 3 more of these over the semester. I'm going to stay at the hand-waving esoteric level. But believe me, that's only a small part of this semester. Most of the semester is going to be very practical, hands-on. But hopefully this background of where we've been and the theories that I'm going to be presenting will make the practical a lot more valuable. So again, we're really thrilled to have you guys in this class with us. We think of it as an honor to have so many of you engaged, and we're going to do our best to make it worth your while. And one of the ways we do that is your feedback. So if you're seeing things that you don't think are valuable, or you see things that are valuable that we may be glossing over, give us that feedback so that we can focus on those things that are most valuable to you. All right. Is the professor in the room?
You're the professor. You should shout at the end.
So we were supposed to go to 9, right?
Yes.
All right, 9 my time. Sorry, I'm in New York. It's a beautiful morning here, by the way. So class dismissed.